Alright, welcome to School of Chemistry. My name is Ogbon Moses Abi. I'll be handling these chemistry classes. This is a popular demand for revision classes for those preparing for JAMB, WAEC, NECO, IJMB. And it's going to be a revision class. We'll take it as detailed as possible just to prepare you very well for these exams. So sit down, relax, and listen. And please don't forget, if you're on YouTube, to subscribe to the channel. If you're on Facebook, please follow us on School of Chemistry. Like, ask your questions in the comment section, and share this video. Welcome. Now today, we'll be looking at organic chemistry. Organic chemistry. Now, what is organic chemistry? Organic chemistry simply is the branch of chemistry that deals with the study of carbon and its compound. Simply the study of carbon and its compounds. So basically, anything that you're dealing with in nature, especially living things, you are dealing with organic chemistry. And there are so many numerous millions of organic compounds in nature. But for you to understand their chemistry, you must understand the chemistry of carbon. Now, carbon is able to form this numerous compound by a concept called catenation. Catenation. What is catenation? It's the ability of carbon atoms to bond together to form long chains. The ability of carbon atoms to bond together to form long chain is what we refer to as what? Catenation. And when carbon docks there, we say it does what? Catenates. The ability of carbon atoms to bond together to form long chain. This is what we refer to as catenation. Now, because basically, why do compounds, elements or molecules react in nature? It's in an attempt to attain stability. They are attempting to attain the octet or the duplex structure. That is the noble gas, the structure of the noble gases. Either the octet or the duplex structure. Now, for carbon, which has atomic number 6, we have the electronic configuration 1s2, 2s2, and 2p6. Or for those that understand the KLM configuration better, you have the first shell taking 2, and then the second shell taking 4 electrons. This is the electronic configuration of carbon. Now, for noble gases, the second shell here, this second shell is expected to have 8 electrons in the outermost shell. Or this shell is supposed to have 2s2 and 2p. Am I correct? No, this is supposed to be 2p4. 2p4, please. Now, this the second shell, that is the second energy level, is supposed to be 2s2, 2p6 to attain the neon core, which is the octet structure for the second energy level. But because carbon is only having 4 electrons in the outermost shell, it can neither accept 4 to become stable, neither will it give out 4 to attain the duplex structure. So the major type of bonding you find in carbon compounds is the covalent bond. The covalent bond. So the major type of bond you find in organic compounds are what? Covalent bond. Be it the ordinary covalent bond or the coordinate or the dative covalent bond. All you will be seeing in organic compounds are what? Covalent bonds. Is what is predominant in organic compounds. Now, we'll look at the electronic configuration of carbon. We'll see the definition of carbon. We're looking at the major type of bonds you can find in organic compounds. Now, I want us to look briefly at what certain terms that will help us understand this organic chemistry very well. One, let's look at what is the homologous series. Homologous series. What is a homologous series? A homologous series, simply put, is a family of compounds that follows a regular structural pattern in which successive members differs by a CH group. A family of compounds that follows a regular structural pattern in which successive member differs by what? A CH2 group. We have different homologous series, but the parent homologous series that we know are the alkanes. The alkanes. They follow the formula CN H2N plus 2. We also have the alkenes that follow CN H2N. The alkynes that follows CN H2N minus 2. These are parents homologous series. Every other homologous series takes from the alkanes to be able to drive all the other homologous series. For instance, when you take the ANE from the alkanes, you add ENE to get the alkenes. You take the ANE from the alkanes away, you have the YNE to have the alkynes. So it is all derived from this parents homologous series. Now, talking about the difference in successive members. The first member of the alkane series has carbon 1. Let's study the alkanes, for instance. The first member of the alkane series is called methane, and I need you to know this very well. Methane has only 1 carbon. That means from the formula it's going to be C into 1, H into 2 times 1 plus 2. And this will give you C1 H2 plus 2. And this will be equals to CH4. That is the formula for methane. Now for the second member with 2 carbon, which is ethane, you're going to have C, N now is 2 carbon, which is 2, into 2 times 2 plus 2. And this will give you C2 H. This 2 times 2, 4 plus 2, 6. Third member, propane. That is 3 carbon. It's going to be C3 H into 2 multiplied by 3 plus 2. And this will give you C3. 2 times 3 is 6 plus 2. H8. Now, let's look at, they say homologous series follows a regular structural formula. This is a regular structural formula, C and H2N. And we're deriving each of the formula. And they say each successive member differs by a CH2 group. So that if you look at C2H6, CH4, what's the difference? 2 carbon minus 1 carbon will give you 1 carbon. 6 carbon minus 4 carbon will give you 6 hydrogen minus 2, 4 hydrogen will give you 2 hydrogen. That's the CH2 difference. Now look at the next successive member to ethane. 3 carbon minus 2 carbon, you have 1 carbon. 8 carbon, 8 hydrogen minus 6 hydrogen, you have 2. So a successive member differs by a CH2 group. So that if I want to write the formula for the fourth member, which is butane, with 4 carbons, I don't need to cram all this. I just come and add CH2 to this. C plus 3 will become C4. 2 hydrogen plus 8 will become H10. And that becomes the formula for butane. Pentane, successive member differs by CH2 group. So if I add the CH2, C plus this will become C5. C plus 2 will become H12. Now, add a successive member now will differ by a CH2 group. To get your hexane, hexane will be C plus 1C plus 5 becomes 6. Then 12 plus 2 will become H14. I'll know that my hexane will have the formula 6,7 H16. Octane will have the formula C8 H18. Nonane will have the formula C9 H20. And then decane will have the formula C10 H22. And this is how it proceeds. The difference between each of these groups is what? A CH2 group. A CH2 group. That is the difference for each of the successive members. This is for the alkyl series. For the alkyl series, if they will follow the formula CnH2n. And now because the alkyl series, each of these homologous series, the determining factor or the difference in each of these homologous series is the presence of a functional group. Like in the alkane, we have the carbon-carbon single bonds. In the alkenes, we have the carbon-carbon double bond for the alkenes. While in the alkynes, we have the carbon-carbon triple bond. This will make the difference. And then when we talk about the alkanols, we have OH. The alkanols is going to be an R attached to OH. While the alkanoic acid or the alkanoic acids denoted by RCOO, R double bonded to O, then H, OH. We have the alkanas denoted by RCHO, and so on and so forth. There are so many functional. We have the alkanoids, we have the alkanones, we have the amides, we have the nitrites. Each of them is determined by what? The different types of functional group present. And what is a functional group? What is a functional group? That brings us to the next topic. What is a functional group? So before we look at what a functional group is, before we look at the functional group, we need to first of all understand what is an alkyl group. An alkyl group simply is a group derived by just a removal of a hydrogen atom from the corresponding alkane. A removal of a hydrogen atom from a corresponding alkane. So the formula from an alkyl group is Cn H2n plus 1. Remember, for alkane is Cn H2n plus 2. So when you remove one hydrogen from alkane, you just have one left. So that if you have methane has CH4. When you remove one hydrogen from methane, you're going to have CH3. I will call this methyl. Remove the ANE of the alkane and replace it with YL of the alkyl. Now, ethane. Ethane, C2H6. Sorry, I want to write it there. C2H6. If you remove one hydrogen, you're going to have C2H5. You call this ethyl. Then we have propane. Propane, C3H8. Move one hydrogen, you are going to have C3H7, and this will now become propyl. Alkyl groups simply are just a part of a compound where other atoms can attach themselves. They generally determine the physical property of that compound. Alkyl group generally determine the physical property of a compound. Now, let's look at what is a functional. What is a functional group? What is a functional group? What is a functional group? A functional group simply is an atom or group of atoms that determine the chemical property of a homologous series. An atom or group of atoms that determine the chemical property of a given homologous series. Now, we have many different types of homologous series. Now let's try to see their functional group. Now, this is going to be the homologous series. Then the functional group. The functional group. Each homologous series, like we have said, have what determine the chemical properties, and that is what the functional group is all talking about. Now, for the alkanes, the functional group is the carbon-carbon single bond. The alkenes, the functional group is a carbon-carbon double bond. For the alkynes, the functional group is a carbon-carbon triple bond. For the alkanols, the functional group is a hydroxy group, OH. For the alkanoic acids, or the carboxylic acids, the functional group is COOH, or you can write it as COOH. For the alkanals, the functional group is COH, or you write it as CHO. We have the alkanones with the functional group CO and O attached to, CO and O attached to an R. That is an alkanone. For the alkanones, the functional group rather is R, C, double bonded O to R. Ethers, the functional group is R, O bonded to R. Esters, going to be R, C, O bonded to R. Amines, we have R bonded to NH2, and so on and so forth. So these are the different functional groups for different homologous series. Basically, what this functional group does is that they determine the chemical properties of a given homologous series. They determine the chemical property of a given homologous series. So now I want us to look at the IUPAC nomenclature of organic compounds. How do you name organic compounds? Now, in naming organic compounds, there is an association that guides everything that happens in chemistry, and that is the IUPAC, who means International Union of Pure and Applied Chemistry. They have set up rules for naming organic compounds. Rule number 1 is how to name your parent hydrocarbon. So how do you do it? You select the longest chain and name it as a parent hydrocarbon. So if I have a carbon skeleton like this, and let's say there is a side chain here, and there is a side chain here. My longest chain is going to be 1, 2, 3, 4. So I'm going to name it after the root hydrocarbon. A 4-carbon compound, like we have seen earlier, is butane. So no matter one functional group is present in it, I'll name it after what? Butane. It's going to be a but. Or you can say start with but, depending on what the functional group now will determine whether it's a butane or not. So let's say but, it's going to be a but. That is 4-carbon compound. And let's say the structure is 3. is going to be a prop. Reason being that if it is not an alkane and the functional group is OH, we know that it is no longer a propane, so it's going to be a propanol. So it's a prop. So you now mix after the parent alkane, depending on the longest chain. You select the longest chain as the root hydrocarbon. Now, when you select the longest chain as the root hydrocarbon, you number the parent hydrocarbon from the side that gives the functional group or the side chain the smallest possible number. Now, when there is functional group, you number it from the side that gives the functional group the smallest possible number. And where there is no functional group and there is a side chain, you know from the side that gives the side chain the smallest possible, because in that instant the side chain is now acting like a functional group, except in situation whereby it's an alkyne with alkene with a double bond or alkyne with a triple bond. Now the triple bond or the double bond now become a functional group. In that case, I have to start numbering from that direction. So now, for instance, if I have a carbon skeleton like this, I have to first of all determine my root hydrocarbon. So my root hydrocarbon is going to be 1, 2, 3, 4. It is a boot. And because there is a double bond, it's going to be a butane. Now, we have to number the side, the root hydrocarbon. You can number it from two sides now. If I decide to number from here, I'll have 1, 2, 3, 4. That is one direction. If I number this way from right to left, right to left, I'm going to have 1, 2, 3, 4. Now, what is our functional group in this case? Our functional group is a double bond, and the rule says you number from the side that gives the functional group the smallest possible number. So, if you start from here, your functional group is going to be either on carbon 4, on carbon 3, or carbon 4. If you number from here, your double bond is going to be on carbon 1. It's not carbon 2, it's carbon what? 1, between carbon 1 and 2, but it's carbon 1 that is the smallest number, so it's on carbon 1. So the smallest number that you can assign to the double bond in this case, the functional group here is 1. So numbering from right to left is the correct direction. But what if I have a structure here? I have 1, 2, 3, 4, 5, 6, and I have a functional group here. You can number from left to right: 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Now, the parent hydrocarbon here is 1, 2, 3, 4, 5, 6. It's a hex. And because there's an O here, it's a hexanol. Now, which direction is correct for numbering? If I number from left to right now, 1, 2, 3, 4, 5, my OH is on carbon number 5. But if I number from left to right, I have 1, 2, and my OH is on carbon number 2. Can you see that? From left to right is on carbon number 5. While from right to left is on carbon 5. While from left to right is on carbon 2. So the direction that gives it the smallest possible, the functional group, the smallest possible number is from what? Left to right on carbon 2. And that is the right direction to number it. And that's how you do it for every other compound. Now let's do for this 1, 2, 3. 1, 2, 3. 1, 2. This is not supposed to be a triple bond, so it's a pentyne. Now, if I number from here, I have 1, 2, 3, 4, 5. If I number from here, I have 1, 2, 3, 4, 5. Now, from left to right, the triple bond is on carbon number 3. While from right to left, the triple bond is on carbon number 2. So the correct direction to there is the side that gives the functional group, which is the triple bond now, the smallest possible number. So it's on carbon number 2. Now let's proceed. Indicate the position of the side chain with numbers, and where a side chain is repeated, use the prefixes di, tri, and so on. So if we decide to use this still as an example, and I have a side chain here, let's say methyl group CH3, and here there is a methyl, a chlorine group, and let's say there is a bromine group here. And then here, I have a methyl group. We say the correct number, direction to number is 1, 2, 3, 4, 5. So on this now, we have one side chain here. Methyl is on carbon number 4, and this methyl is on carbon number 5. So I know that I have a methyl on carbon number 4 and a methyl on carbon number 5. So it's going to be 4, 5. There's a methyl on carbon 4 and a methyl on carbon. So you say 4, 5. And because there are 2, you say dimethyl. That's one functional group present. There's a bromo on carbon number 4. So I'm going to say 4 bromo. 4 bromo. And then there is a chlorine on carbon number 1. So we're going to have 1 chlorine. So you have to pick all your side chain and indicate their position with number. And when they are repeated, you do what? You indicate with prefixes like that. Now, let's look at another example. Alright now, like in this compound now, we have the side chain chloro, methyl, bromo, methyl, and then this is the functional group. And then we have the ion group. So we number from the side and give the functional group the smallest possible number. And it has to be from this side. 1, 2, 3, 4, 5, 6. My parent alkane is a hex. It is a hex. So now, because that is it, let's get the side. What we are doing is just a skeletal representation. Let's get the side chains out. Now, on carbon 1, I have chlorine. And there's no that chlorine. No carbon 6 rather. So I'm going to have 6 chloro. Now, I have another substitute, bromo on carbon 5. So I'm going to write 5. I have a bromo on carbon 4. I have another bromo on carbon 4. And there are 3 bromo altogether. So I'm going to have tri-bromo because there are 3. Now after that, I have a methyl here on carbon 6. Normally, the smaller number should come first. It's the right thing to do. So it's going to be 4, 4, 5 trimethyl. Then I'll have methyl on carbon 6 and methyl on carbon 3. So it's going to be 3, 6 dimethyl. Then we have iodine on carbon number 1. So it's going to be iodo. 1 iodo. Now, the last rule say write the name of the side chain chains in alphabetical order. Now look at these side chains that we have. We have a chloro, we have a bromo, then we have a methyl, we have an iodo. So alphabetically, we have C, we have B, we have M, we have I. So B comes first. So if I'm naming this compound, I'm going to say 4, 4, 5 tri-bromo. Followed by C, 6 chloro. We have now M and I left. I comes before M. So we're going to have 1 iodine. And then what is left? Methyl. 3, 6 dimethyl. Now we'll come and name it after the parent alkane. And because this is a 6 compound, 1, 2, 3, 4, 5, 6. Attached to our functional group is going to be hexanol. I'll leave it as hexanol now, but when we go deeper, you understand that this is not a hexanol only, it is actually a hexan 2, or telling you that the position of the OH is on carbon number 2. A hexan 2 is different from a hexan 1 and different from a hexan 3 because of the position of the what? Functional group. And you must indicate that in your what? Nomenclature. So let's go into the naming of compounds properly. Let's take examples and name them, and let's see how it is done. Alright, let's try to name these compounds. This is 1, 2, 3. Now remember the rule, you choose your root hydrocarbon and name it the parent hydrocarbon. So in this case we have 1, 2, 3. So it's going to be a prop, and because they are single carbon bond is an alkane. Now we number them From each direction, we'll give the side chain the same number. So 1, 2, 3. The number is 2. Now you take the position of the only side chain present, which is methyl. So I'm going to name it 2. Methyl. Propane. I'm exhausting this pen. 2-methyl propane. So that is how to name that compound. Now let's look at this compound. This compound, you take the root hydrocarbon 1, 2, 3, 4, 5, 6. There are 6. So it's a 6-carbon compound. But because there is a double bond, it's not going to be hexane, but this time it's going to be what? Hexene. Now a number from the side, I give the side chain the smallest possible number. If I number from up, 1, 2, 3, 4, it's going to be on carbon 4. But if I number from there, I'm going to have 1, 2, it's on carbon 2. So from this direction is better. 1, 2, 3. 4, 5, 6, carbon 2, carbon 3, carbon 1. So we have to name the side chain present. So we have to name them alphabetically. We have a methyl here, we have a chloro here, and we have a bromo. So we'll start naming with the bromo. We have bromo on carbon 5, and bromo on carbon 1. So we're going to say 1, 5. Because there are 2, we say di-bromo. Then we also have a chloro here, chloro and methyl. Chloro comes before methyl alphabetically. So we have chloro on carbon 2, chloro on carbon 3, and chloro on carbon 4. So we're going to have 2, 3, 2, 3, 4, trichloro. Then we have just a single methyl on carbon number 5. 5 methyl. Hex. The double bond is on carbon 2. So we're going to say hex 2 in, telling us that the double bond is on carbon 2. If the double bond was to be on carbon 1, it's going to be hex 1 in. If the double bond is on carbon 4, it's going to be hex 4 in, depending on the position of the double bond. Now let's look at this one. 1, 2, 3, 4, 5. 5. So how do we name this? We name from the side that give the functional group the smallest possible number. So number from here 1, 2, 3, 4, 5. Now 1, 2, 3, 4, 5. We have a side chain here, a methyl and a bromo. So we'll name them alphabetically. So we're going to say 3. Bromo comes before methyl alphabetically. So it's going to be 3 bromo, 2 methyl. 1, 2, 3, 4, 5. Our parent alkane is a pentan. The OH is on carbon number 1 O. Correct it pent, 1 O, pentan, 1 O. Anyone is correct. So that is how to write name organic compounds. That is how to name organic compounds. Alright. Now that we know how to name organic compounds, let's see how we can translate the name of organic compound back to a structure. We'll start with this first one, 2,2-dimethyl butane. Now, since it's a butane, they have told us that the parent hydrocarbon is a 4-carbon compound. So it's going to be, I'm going to write my 4-carbon compound. 1, 2, 3, 4. These are 4-carbon compound. But they say on this 4-carbon compound, we have a methyl group, 2 methyl group. All of them are on carbon 2. So I can put my methyl group here, 1, CH3, on my pen. CH3. Now, these are 2,2-dimethyl. Now we can fill the rest with hydrogen since it is a butane. There's a hydrogen here, and then 3 hydrogen. These are 2,2-dimethyl butane. 2,2-dimethyl butane. Now let's look at the name 1-chloro 2-methyl pent 2-ene. 1 chloro, 2-methyl pent 2. We have to write the parent structure first. The pent 2-ene. Since it's a pent, it's a 5-carbon compound. 1, 2, 3, 4, 5. Pent 2-ene. So this is 1. Shit. Okay, pause. And so because it is a pent, it's a 5-carbon compound. So we'll name from here 1, 2. This carbon number 2 is a pent 2-ene. So the double bond is here on carbon number 2. And because we have our chloro on carbon number 1, we're going to say chloro here. And then we'll have methyl on carbon number 2. So our methyl is here. So that is all. We need to fill the rest with hydrogen. We fill the rest with hydrogen. 1, 2. Remember, your carbon atom cannot carry more than 4 bonds. And that must always be a rule that you go at 1, 2, 3, 4 at the back of your mind. 1, 2, 3. Add 1 hydrogen, 1 hydrogen, 1 hydrogen, 3 hydrogen. Now, the last one. 2, 2, 3. Tribromo, 4 chloro, 3 methyl pentan, 1 or it's a 5-carbon compound. So I'll write 1, 2, 3, 4, 5. Pentan 1 or on carbon number 1. OH is there. Now, so if I start from here, this is 1, 2, 3, 4, 5. They say on carbon number 3, I have a methyl, CH3. On carbon number 4, I have a chloro, Cl. Then on carbon number 2, I have a bromo. So here it's going to be Br. And then another bromo on carbon number 2, another Br. And then on number 3, I have another period. These are the 3 bromo atoms. Now we can fill the rest with what? Hydrogen. So here I'm going to have 1 hydrogen, 3 hydrogen, and then here 1, 2, 2 hydrogen. And everything now is satisfied. Let me give you a take home. Alright, take home. Name the compound below. CH3, CH, CH, CH3, CH3, CL. Please name it. Let's have the answer in the comment section. And if you have any question, don't forget to drop it in the comment section. Please, if you're on Facebook, follow us on School of Chemistry, like and share our page. If you are following us on YouTube, please don't forget to subscribe. We'll follow you on the comment section so that we can attend to your question. You can always reach us. If you want the private section with this, reach out to us. Thank you.